Good afternoon, and thank you to Rick Burns of NDH Consultants for the invitation to speak today on PFAS impacted biosolids management. PFAS are a large and complex and ever-expanding group of manufactured chemicals that are used to make a wide variety of consumer products, from cookware to clothing and carpets to products used in the aerospace, automotive, electronic, and military industries. PFAS molecules are made of a chain of linked carbon and fluorine atoms. Because of the strength of the carbon-fluorine bond, these chemicals do not degrade in the environment. We can categorize PFAS chemicals based on their functional groups, the sulfonates and the carboxylates. We can also categorize them based on their chain length or number of carbons. PFOS and PFOA have been manufactured for the longest time, are the most widespread of the PFAS chemicals in the environment, and are the most well studied. Both have 8 carbons or a chain length of 7. The third major class of compounds are the telomeres. The difference between these chemicals and the sulfonates is the addition of 2 carbons that are not bonded to fluorine atoms. Hence, as you see here, the carbon-hydrogen functional groups. Hence, these are called polyfluorinated PFAS rather than the perfluorinated compounds. One of the major challenges with the PFAS chemicals is their sheer number. There are more than 4,700 PFAS chemicals, and the number continues to increase as we create new forms of this type of chemical. Now, we've dealt with groups of chemicals before, and I thought it would be beneficial to compare PFAS to PCBs. On the contrary, there were only 209 congeners of PCB, and the properties of this group of chemicals is much more similar. For example, the solubility of PCBs varies by roughly 2 orders of magnitude. On the other hand, the solubility of PFAS varies by roughly 20 orders of magnitude. Before we continue, let's discuss how PFAS chemicals end up in biosolids. The major components of municipal waste are municipal sewage, stormwater, industrial discharge, and landfill leachate. Some of the most common industries that can result in the release of PFAS into industrial discharge are plating operations, leather and fabric treating operations, tanneries, paper and packaging manufacturing, and the manufacturing of parts with Teflon-type coatings. Now, we can attempt to control the release of PFAS chemicals from industrial discharge and landfill leachates using the industrial pretreatment program. Controlling the release of PFAS chemicals from municipal sewage and stormwater is much more difficult. PFAS chemicals can accumulate in the biosolids from both primary and secondary sludge. The solids from the pretreatment processes tend to end up in the landfill. In this talk, I will focus on source reduction and biosolids treatment, both with the goal of keeping PFAS out of the environment. Source reduction includes the industrial pretreatment program, along with liquid treatment technologies, and biosolids treatment includes digestion, incineration, pyrolysis, gasification, and supercritical oxidation. There are other processes, but these are the most common, and we simply just don't have time to cover all of the treatment processes. With regard to source reduction, we will first look at the industrial pretreatment program. We will focus predominantly on field-tested liquid treatment and then briefly discuss some of the novel liquid treatment processes. The Industrial Pretreatment Program initiative mandated that all municipal wastewater treatment plants in Michigan with required IPPs determine the effluent concentrations of PFOS and or PFOA in order to determine if there were releases to surface water or groundwater. And if found, these wastewater treatment plants were required or are required to reduce and eliminate any sources. If the levels exceed the screening criteria, additional efforts are required. So roughly 45% of wastewater treatment plants in Michigan were found not to have sources of PFOS or PFOA. Roughly 45% were found to include such sources. About a quarter of these of the wastewater treatment plants were found to meet water quality standards, whereas about a third, 31%, did not meet the water quality standards and require additional efforts. Now let's look at the treatment technologies. The most commonly used liquid stream treatment method is granular activated carbon or GAC. It is effective for the removal of long-chain PFAS. Now, for shorter chain PFAS, lower loading capacities result, along with faster breakthrough times. One of the major challenges of granular activated carbon and also powdered activated carbon is the fact that other organics and even some of the metals will sorb onto the surface of the activated carbon and compete for surface sites. And many of these compounds are found in much higher concentrations than are the PFAS. As such, treatability studies are needed, and as you can see in the table below, the level of removal varies significantly, and much of that is because of the water quality parameters in the system that is being treated. Now, one of the major challenges with GAC is what to do with the spent activated carbon. It can be regenerated. It can also be incinerated, but that has its own issues, as we will discuss in a bit. This table demonstrates the effectiveness of granular activated carbon for the removal of PFAS. Granular activated carbon was implemented at a number of sources as part of the industrial pretreatment program. And it can be noted here that for 5 of the 7 sites, greater than 97% reduction was achieved. However, as you note, for the last 2 sites, the level of reduction was significantly less, likely due to the water quality parameters, but we don't have the data, or I don't have the data at this point, and we don't have time to explore the reasons for these differences. But again, I want to emphasize the importance of treatability studies in order to design these systems. Ion exchange resins are used to remove ionic species, and the PFAS chemicals are typically anionic in aqueous solution. In addition, sorption may occur due to the hydrophobic interactions between the resin and the nonpolar ends of the PFAS molecule. Higher selectivity and single-use ion exchange resins can be used to selectively target the more mobile compounds. And typically, ion exchange resins will have greater capacity, faster kinetics, and a lower empty bed contact time than does GAC. However, like with GAC, there is simultaneous removal, in this case, of other anionic species, competition reactions that can reduce the capacity of the ion exchange resin for the target compounds. And that's one of the reasons why you see such variability in the table that's shown here. Again, with ion exchange resins, we have similar problems or challenges as we do with granular activated carbon. What do we do with the spent resin? Do we incinerate it? Do we regenerate? How do we process this material? And this figure here really just exemplifies again the variability in removal of these chemicals on an ion exchange media. The last of the more common methods that we'll talk about is reverse osmosis. Reverse osmosis is a pressure-driven process. It is highly effective for longer chain PFAS. However, one of the major challenges is fouling. The deposition of organic matter on the membrane surface. Another challenge is scaling, which is the deposition or precipitation of inorganics on the membrane surface. As a result, pretreatment is necessary, and also post-treatment is also required because of the corrosivity of the product water from reverse osmosis. With ion exchange and activated carbon, we had a solid media that we needed to either regenerate or dispose of. Here we have a reject stream that is an aqueous phased concentrate. And you can see that with reverse osmosis in general, we get greater than 90% removal of the PFAS chemicals. We don't have time to consider all of the processes used for the treatment of liquids, but some of the ones that are in the developmental stage are alternative sorbents, conventional water treatment processes, precipitation, coagulation, flocculation, nanofiltration, also a pressure-driven process that doesn't operate at as high of pressures as reverse osmosis, redox processes. Much effort has gone into the development of both oxidative and reductive processes, although now there's a significant effort that's really being placed in more of the reductive processes in order to defluorinate these compounds. Additionally, biodegradation has been studied, attempting to find an organism that is capable of degrading the PFAS chemicals. Foam fractionation has been used along with deep well injection. And just as a reminder, deep well injection is not a treatment technology, but it has been considered as a way of disposing of the liquid concentrates. As mentioned previously, one of the major challenges with GAC and ion exchange are how to deal with the spent carbon and resins. We can regenerate these. However, when we do, the PFAS chemicals end up either in the air or in a liquid stream. We can incinerate them, and we'll discuss that shortly with regard to biosolids, but the issues are the same. And we can stabilize and solidify. And stabilization, solidification has been used extensively to contain radioactive waste, but to a lesser extent with hazardous waste, unless they're mixed waste, which is radioactive and hazardous. Let's look at the concept of using stabilization solidification for spent carbon or ion exchange resins. So shown here, we have 3 columns. The third is not being used at the present time. So we start operating, and the exchange or the adsorption zone moves down the column, and eventually we've exhausted that resin or the activated carbon. At that point, we can isolate the first column. The second column becomes the first column, and the additional column becomes our second column. We take that first column and material, and we can look at stabilizing and solidifying that material. Thus, stabilization solidification involves the conversion of PFAS into less soluble, less mobile forms. Cementitious stabilization solidification is one of the most widely used techniques for the treatment and ultimate disposal of mixed waste and also low-level radioactive waste. Sulfur cement has a number of advantages over Portland cement. Sulfur concrete has higher compression and tensile strengths. The full strength of this material is reached in hours rather than in weeks. The process has been widely used for radioactive, hazardous, and mixed wastes. The loading rates tend to be greater than that for the cementitious processes. Both thermoplastic and thermoset polymers have been successfully used to microencapsulate radioactive waste. Thermoplastic extrusion using low-density polyethylene has been used for polymer encapsulation of mixed waste. Thermoset polymers, including epoxies, are formed by a chemical reaction involving a liquid monomer and a curing agent. Metal catalysts have also been used. This process is exothermic, and constituents in the waste can interfere with the chemical reactions. As a result, this process tends to be less desirable than thermoplastic encapsulation. Some of the challenges are fugitive emissions, especially with exothermic reactions. And this process requires extensive testing to ensure that the PFAS chemicals are not leaching from the stabilized solidified material and would not move into the environment. Moving on to biosolids treatment, as I mentioned, we'll look at these 5 processes. Conventional wastewater treatment technologies have been reported to be relatively ineffective in removing the PFAS chemicals from wastewater. Mass balances on several full-scale wastewater treatment plants have shown that there's actually an increase in the mass flows of the shorter PFAS chemicals, and this is thought to be due to the transformation of the fluorotelomere alcohols into lower molecular weight PFAS. The transformations have been found to be dependent on solids retention time of the upstream processes and also in the digester. Unfortunately, the mechanisms of these transformations are poorly understood, both for aerobic digestion and for anaerobic digestion. The incineration of PFAS chemicals requires temperatures in excess of 1,000 degrees C and residence times in the range of 2 to 4 seconds. Compounds such as carbon tetrachloride require even higher temperatures. In a recent EPA presentation, it was reported that 99.9% destruction of fluoropolymers was achieved with hydrogen fluoride formation. The hydrogen fluoride formation supports the cleavage of that carbon fluorine bond. So also no detection of perfluoroalkyl acids in the emissions from this process. As far as I am aware, however, there were no full-scale applications implemented specifically for PFAS incineration. As with all incinerators, stringent air permitting is required. Particulates can be removed with scrubbers, electrostatic precipitators, or baghouse filters. NOx, SOx, and various organic chemicals can be produced, and these would need to be removed. And in addition, a base needs to be added in order to manage the hydrogen fluoride that is generated from the process. And finally, syngas, carbon monoxide, and hydrogen may be produced and then cycled back to the system as fuel. As I mentioned, one of the biggest challenges of incineration is the need to monitor and characterize the emissions for products of incomplete combustion. And these include the shorter chain PFAS, partially fluorinated PFAS, etc. The nature and amount of these products of incomplete combustion depend on such factors as temperature, fuel to oxygen ratio, residence time in the incinerator, physical state of the product, and the catalyst that is used. Pyrolysis is defined as the chemical decomposition of organic materials at high temperatures, typically above 450 degrees C, in the absence of oxygen. The products include pyrolysis gas or syngas, hydrogen again, carbon monoxide, also carbon dioxide. Bio-oil is produced, which can be used for energy production, and biochar can be land applied. The disadvantages of pyrolysis is still in the developmental stage for PFAS, and there are concerns about the high cost of treatment. Gasification is similar to pyrolysis. However, it's conducted at higher temperatures and in the presence of oxygen. The residence times are slightly less than with pyrolysis. Residence times of 2 to 3 seconds are necessary. The products are syngas and biochar. However, research still needs to be done in order to ensure that there is a fluorine mass balance and to show that cleavage of the carbon-fluorine bond actually occurs. Supercritical oxidation is an advanced oxidation method that uses water above its critical point, that is 374 degrees C and 221 bar. At these conditions, the presence of oxygen in the presence of oxygen, that oxygen reacts with the organics, converting them to water, CO2, inorganics, and heat. A study conducted by Duke University researchers demonstrated 99.9% destruction of 9 PFAS chemicals. Similarly, a study of looking at PFAS in lime stabilized sludge showed similar removal levels. The disadvantage of supercritical oxidation is that in these harsh environments can result in corrosion and also the leaching of heavy metals into water. So in summary, reducing PFAS at the source is the most effective means of mitigating PFAS in biosolids. GAC, ion exchange, and reverse osmosis are presently the most commonly employed techniques for PFAS removal from liquid streams. However, there is a need to develop methods to deal with the residuals and/or the concentrates produced in a sustainable way while avoiding unintended consequences, including the presence of PFAS in biosolids or the formation of other fluorinated compounds. Thank you. And I'm happy to answer any questions you may have. And Here are the list of references used in preparing this presentation. Thank you and have a great day.